So we suppose that the n by n matrices A and B commute, which means that AB equals BA, and we need to prove that e to the power of A plus B equals e to the power of A plus times e to the power of B. Also, the suggestion is given that we can group the terms in the product of the two series on the right-hand side to obtain the series on the left. We also need to deduce from the result of above problems that for every square matrix A, the matrix e to the power of A is non-singular with e to the power of A inversed equals e times to the power of negative A. This is for square matrices. Well, so let's consider 2 by 2 diagonal matrices A and B, which commute. So let A be equal to A1, 0, 0, B1, and B equals A2, 0, 0, B2. Then A to the power of n equals A1 to the power of n, 0, 0, B1 to the power of n, and B to the power of n equals A2 to the power of n, 0, 0, B2 to the power of n. So for integers n which are equal or larger than 1, we have that e to the power of A equals identity matrix plus A squared over 2 factorial plus A to the third power over 3 factorial, and so on. So we will put the values and we get that e to the power of A equals identity matrix 1, 0, 0, 1 plus our A matrix, which is A1, 0, 0, B1 plus plus A squared over 2 factorial, which is A1 squared over 2 factorial, 0, 0, B1 squared over 2 factorial, and so on. And this equals matrix with entries 1 plus A1 squared to the over 2 factorial plus so on, 0, 0, 1 plus B1. So we have just added these three matrices, plus B1 squared over 2 factorial, and so on. So this equals e to the power of A1, 0, 0, e to the power of B1. So we can see that the exponential of the diagonal 2 by 2 matrix A is obtained by exponentiating each diagonal element of matrix A. Similarly, for matrix B, e to the power of B equals e to the power of A2, 0, 0, e to the power of B2. Well, now let's look at e to the power of A times e to the power of B. It equals this matrix times this matrix. Now we just do the multiplication of these matrices and we get e to the power of A1 times e to the power of A2 plus 0, 0, 0, and e to the power of B1 times e to the power of B2 plus 0. And this equals e to the power of A1, e to the power of A2, 0, 0, e to the power of B1, e to the power of B2. And you can see this equals e to the power of A plus B. So we have proven that e to the power of A times e to the power of B equals e to the power of A plus B. Since e to the power of A is e to the power of A is this matrix, then in order to find its inverse, so e to the power of A inversed equals 1 over a to the power of a1 times e to the power of b1 multiplied by e to the power of b1 0 e to the power of a1. So here we get 1 over e to the power of a1 0 1 over e to the power of b1, and this equals e to the power of negative a1 0 and e to the power of negative b1. So now let's look at e to the power of negative a, which equals identity matrix minus a1 o b1 plus a1 squared over 2 factorial 0 and b1 squared over 2 factorial minus and so on. This whole thing equals e to the power of negative a1 0 e to the power of negative b1, and as you can see, these two things are the same. So we have proven that e to the power of a inversed equals e to the power of negative a.